Hello students, welcome to the class of number system where we are going to learn how typed information is converted into commands for a computer. So let's get started. Just like we have a common language, English, that we use to communicate and understand each other, computers understand only machine language that we can use to communicate with them. Before execution, they convert the instructions written in a programming language into machine language. This machine language comprises of numbers. So, a number system is a mathematical notation for representing a number, and it is used to represent the numbers in the computer system. Let's begin learning about number systems. Number system is a way to represent the numbers which in turn represent a quantity. For example, to represent the number of students in a class or the number of subjects taken by a student, every number system has a set of digits. There are basically 4 types of number systems which are used to represent different data values. Decimal number system, binary number system, octal number system, and hexadecimal number systems are the 4 systems. Let's start with the first type of number system, which is the decimal number system. The number system that we use in our day-to-day life is known as the decimal number system. It has base 10 as it uses 10 digits from 0 to 9. In this, the successive positions to the left of the decimal point represent units, tens, hundreds, thousands, and so on. Because of the 10 digits in this number system, its base or radix is 10. It is also a positional number system. This means that each position represents a specific power of the base, which is 10. For example, the decimal number 1234 consists of the digit 4 in the units position, 3 in the tens position, 2 in the hundreds position, and 1 in the thousands position, and its value can be written like this. Thus, we can say that the value of each digit in a number depends upon some criteria which are mentioned below: the face value of the digits, the base of the number system, and the position of the digit in the number. In our example, the face value of the number is 1, 2, 3, 4, and the place value for the number 4 is ones followed by next number 3, whose place value is tens, 2, whose place value is hundreds, and 1, whose place value is thousand. The rightmost digit is called least significant digit, LSD, as it is the smallest according to the place value, which is units, while the leftmost digit is called the most significant digit, MSD, as it is the biggest number according to the place value, which is 1000. That is the decimal number system. Let's now see what is binary number system. The binary number system consists of only 2 digits, that are 0 and 1. So the base of the binary number system is 2. Just as each position in a decimal number has a place value associated with it, so does each position in a binary number. In binary, the place values moving from right to left are successive powers of 2. So 2 is to 0, 2 is to 1, 2 is to 2, 2 is to 3, or 1, 2, 4, 8. For example, in a 4-digit binary number, the binary place values are 1, 2, 4, and 8. Thus, we can say that a value of each digit in a number can be determined using the digit, the position of the digit in the number, and the base of the number system, that is, the total number of digits available in the number system. Let's look at how converting binary number into decimal number works. The binary number 11,000 can be converted to its decimal number, which looks like this. So 11,000 is a binary representation of decimal system number 24. Moving on to the third type, which is the octal number system. In this, the base is 8. Hence, there are only 8 symbols of digits: 0, 1, 2, 3, 4, 5, 6 and 7. The largest single digit is 7. Each position in an octal number represents a power of the base 8. Let's look at the converting of octal numbers into a decimal number. The procedure is similar to binary to decimal conversion. The only difference is in the change of the base. Now, let us find the decimal value of the octal number 45. Thus, it can be converted to its corresponding decimal like done here. Now on to the converting of octal number into binary number. To do that, let us convert the octal number 545 to its corresponding binary by referring to the truth table. Using it, you will get this. 54 into 8 is equal to 101, 100, 101 into 2. And now we have our fourth and last, the hexadecimal number system. It uses 16 digits including 6 letters of the alphabet, which is where its name comes from, because hex means 6. These digits and letters include the symbols 0 to 9 and letters A to F. The table below shows numbers in different number system. Now we will see the converting of hexadecimal numbers into decimal numbers. For this, let's find the decimal value of the hexadecimal number 4a. Thus, the hexadecimal number 4a can be converted to its corresponding decimal like so. Like we've been seeing, each number system can be converted to another. So let's continue this time to decimal to binary conversion. This is a method of successive division. Step 1 is to divide the given decimal number by 2 and note down the remainder. Now, divide the obtained quotient by 2 and note the remainder again. Step 3 is to repeat the above steps until you get 0 as the quotient. Step 4 is write the remainder in such a way that the last remainder is written first, followed by the rest in the reverse order. Lastly, this can also be understood in another way, which states that the least significant bit of the binary number is at the top and the most significant bit is at the bottom. This number is the binary value of the given decimal number. Let's look at an example of this conversion where we will convert decimal number 13 into its binary equivalent. Step 1 is to divide the given number 13 repeatedly by 2 until you get 0 as the quotient. Step 2 is to write the remainder in the reverse order. After calculating the remainders, we will write them in such a way that the most significant bit of the binary number is written first, followed by the rest. Therefore, the binary equivalent for the given decimal number 13 is to 10 is 1101 by 2. Let's now see the conversion of binary to decimal. Step 1 is to list out the powers of 2 for all the digits starting from the rightmost position. The first power would be 2 raised to 0, and as we move on it will be 2 raised to 1, 2 raised to 2, 2 raised to 3 and so on. Now multiply each digit in the binary number starting from the right with its respective weight based on its position and evaluate the product. Step 3. Finally, sum up all the products obtained for all the digits in the binary number and express the binary number as a decimal number. Let's see an example where we will convert binary number 1101 by 2 into its decimal equivalent. So let's follow all the steps and see what we get. Another way of showing the above conversion is this, and this is what we get. Moving to converting hexadecimal numbers into binary numbers. The hexadecimal systems consists of 16 symbols, so it has a base of 16. This table displays the binary equivalent of hexadecimal numbers. Let's take an example where we need to convert the hexadecimal number A86F to its corresponding binary by referring to the previous table, which will give us this answer. And the answer is... That's amazing! Moving forward with converting decimal numbers to octal. Let us see how to convert a decimal number to its equivalent octal number using the remainder method. In this method, divide the decimal number by 8 recursively until the decimal number cannot be divided further. Then, record the remainders in reverse order to get the equivalent octal number. Taking the example of finding the octal value of the decimal number 12,345 using the steps to convert decimal number 12,345 to its octal equivalent, we get the octal equivalent of 12,34,510, which is 3,718. Let's see the representation here. Now on to converting decimal numbers to hexadecimal. Let us see how to do this using the remainder method. In this method, divide the decimal number by 16 recursively until the decimal number cannot be divided further. Then record the remainders in reverse order to get the equivalent hexadecimal number. So let's take the example and find the hexadecimal value of the decimal number 12,345. Next is conversion of octal and hexadecimal to decimal. The process of conversion of octal and hexadecimal is simple. Here, each digit of the given numbers is taken from the extreme right, which is the ones place, and multiplied with its base, with the index in increasing order, starting from 0 onwards. The process continues till all the digits are exhausted and then added up. Let us consider this example and convert 175 by 8 into its decimal equivalent. And we get this. Then we have the conversion from binary to octal. Here, groups are to be made, consisting of 3 digits each from the extreme right of the number. Then, the decimal equivalent of each group is to be found and written together to get the octal equivalent. Note that 0 was placed to the left of the MSB to produce groups of 3 bits. This is the conversion that can also be used. The example is converting this number to octal. Here, 110, 101 and 111 are the binary equivalents of 6, 5 and 7 respectively. Therefore, the octal equivalent is 6,578. After this is conversion from binary to hexadecimal. Here, groups are to be made, consisting of 4 digits each, from the extreme right of the number. Then the decimal equivalents of each group are to be found, and when they are written together, what we get is a hexadecimal equivalent. Let's follow this conversion table. Now, moving on from types of number systems, let's now learn about computer arithmetic. Since computers understand only one language, which is the binary language, all instructions provided by the user needs to be converted into the binary language so that they can be processed by the computer. Let us explore the arithmetic operations performed on binary numbers, which are binary addition and binary subtraction. Binary numbers can be added and subtracted as decimal numbers. On adding or subtracting the binary numbers, the result is also a binary number. One method of adding and subtracting is to convert the binary numbers to equivalent decimal numbers and then add or subtract. The rules to add the binary numbers are these. In the fourth case, a binary addition is creating a sum of 1 plus 1 is equal to 10. That is, 0 is written in the sum column and a carry of 1 over to the next column. An example is where we will add 101 by 2 and 101 by 2, which will look like this. On the other hand, the rules to subtract binary numbers are as follows. The number is borrowed when 1 is subtracted from 0. 10 minus 1 is equal to 1. An example for this is to subtract 1 by 2 and 0 by 2. Next is binary multiplication. The rules for performing multiplication using binary numbers is the same as that of the decimal numbers. The given table illustrates the multiplication of two binary digits. An example would be to multiply this number with this, which would look like this. Lastly, in our chapter, let's see binary division. The method to perform division of two binary numbers is the same as that of decimal numbers. An example is to compute this number with this. And that's it, students, for our chapter Number System. Let's meet very soon to explore more exciting concepts. Until then, see you!